In this video, we're going to talk about how integrals are actually just derivatives backwards. So the focus of this lesson is going to be a theorem called the fundamental theorem of calculus, or FTC. So by the end of this lesson, you should be able to answer the following little question: how are integrals related to derivatives? And by the end of Unit 4, which is our last unit in this course, you should be able to answer the following big question: how do we find the areas of weird shapes and then make it easier? So the area part was sort of lesson 18 with the rectangles, and now from here, this is going to be the start of making solving integrals easier. So let's warm up and summarize what we've learned so far this semester in a couple of sentences. So, well, maybe we don't do sentences, maybe we just do words. So we've done limits, derivatives, we've done tangent lines, etc. So we've done a lot of stuff. And what I kind of want you to start thinking about is that all of these things are very closely interrelated. So we've seen like derivatives, tangent lines are very closely related, right? Like the derivative is the slope of a tangent line. Or we can say a derivative is the limit of the slope of a tangent line. So really all of these three words are very interrelated. So what I want to show you now is what I call the map of calculus. So it's a very abridged map. It's not super detailed, but this is how I view the subject of calculus in a very broad sense. So when we teach you calculus, we have to teach you in a linear fashion, right? We have to teach you like one lesson after the other, because that's just how classes are set up, and there's no real way to, teach it not linearly. But in reality, everything in calculus is all interrelated, and it's not like one thing really has to come one after the other. They could be all different and jumbled up and, whatever. So what I want you to see in this diagram is basically we have three big topics: derivatives, integrals, and limits. And within those topics, we have some other topics. But we also have these things that kind of go between topics. So that's a lot of your theorems, like MVT, EVT. We connect limits and derivatives using the limit definition. We connect limits and integrals again using the limit definition. But so far, we don't have anything that goes in between derivatives and integrals. So the only way we have to get from derivatives to integrals is to go all the way through limits. And that's kind of tough. So it'd be really nice if we had an easier way to go directly from derivatives to integrals and vice versa. And that's what we're going to talk about today. So one side note before we move on, this map situation on the screen is what's known as concept mapping. So you can look that up. It's a very common thing to do, but it is a great way to study for your final. So what it allows you to do is it allows you to organize topics in a way where you see the interrelationships between them so that it's less to memorize. So you realize that like actually maybe two topics that you thought were different are the same. So it's kind of like the exercise we did with the flow charts and limits. Kind of the same thing. So you're like mapping out how calculus is structured. So we might include some activities like that in the final review. We'll see how I'm feeling that week. So let's actually jump in and talk about what the fundamental theorem of calculus is. So mathematically, we say if we have a continuous function, then we have two different parts, which we typically call FTC1 and FTC2. But I've put them together for you because I think that it gives you more of a cohesive view of what this theorem actually does. Okay, so if we have a continuous function on the interval a to b, then if we define a function, so we're going to break down what this thing is right here. So this is a function, g of x, and it's defined in terms of an integral, okay? And the variable that we plug in is one of the integral bounds, if you notice. So x is in one of the integral bounds. So we get that. We say that that's actually continuous. So we're saying like the area under the curve is continuous. it's differentiable on the open interval, and if we take the derivative, we just get the function inside of the integral back. Okay? So that's what this part means. G prime of x is equal to f of x. So that sort of function is a little bit tough to wrap your head around at first. I'm going to see if I can make an interactive thing to kind of show you how those functions work. I think I should be able to do that. But for now, let's talk about what that means translated. So we kind of said it a little bit, but basically what that first part is saying is if we take the derivative of an integral, it cancels the integral with maybe a possible chain rule, but we'll talk about that in a minute. So the point of the matter is, if you're given a function in terms of an integral, you take the derivative is going to cancel the integral. Okay. FTC2 is arguably more important for you just because of the types of problems you're going to have to do in your homework and such. But basically FTC2 says we can evaluate integrals in a super, well, I don't want to say easy because sometimes it's actually very hard, but a very straightforward way. So basically what we do is we just undo derivatives. So we undo derivatives, we plug in the integration bounds, and we subtract them. And so when we undo a derivative, we call that function an antiderivative, and that's all that this is right here. So we're saying that big F is an antiderivative of f, so it means that f prime is equal to little f. Okay, so to look a little bit closer at antiderivatives, because that's a tricky thing to wrap your head around, we're going to do a couple of very small examples. So the question to ask yourself when doing antiderivatives is, what function has blank as its derivative? Okay, so let's look at number one. So we have f of x is equal to cosine of x. So if we ask ourselves what function has cosine of x as its derivative, well, you tell me sine of x, right? And that comes straight from our lesson 7 table. So those facts, you should be really quick with knowing them by now. Number 2, we have little f of x is equal to sine of x. So this one gets slightly trickier because if we ask ourselves what function has sine of x as its derivative, you might be tempted to say cosine. However, recall that cosine's derivative is negative sine. So if we go backwards like that, well, we better have a negative sign on the cosine. And this is where antiderivatives can get slightly tricky because the negative signs on the trig functions are different from the derivative rules. Kind of the opposite, really. And if we look at the third one, we have little f of x is equal to e to the x. So if we ask ourselves, what function has e to the x as its derivative? Well, you'd tell me e to the x, I hope. Okay, so those are some examples of antiderivatives. We'll talk about those a little bit more in lesson 20. This is definitely not as far as we can go with antiderivatives, but it's just the concept to get you thinking about it. So now, going all the way back to lesson 7, you may not remember, but I promise it's in your notes. You can go back and look if you want. We briefly mentioned that it's useful to think of differentiation as an operation, just like addition, subtraction, multiplication, or division. And so I think when you view it like this, and you view integrating as an operation as well, then you can kind of relate these two things back to things you already know, right? So it makes more sense as to why certain properties are true or why we can do certain things with them but not other things, because they're just like addition and subtraction. So like addition and subtraction are opposites, right? Multiplication and division are opposites. Squaring and square rooting are opposites. So the idea is that differentiation and integration kind of obey these same rules as these other operations. They're related in such a way where if we do one operation and then do the other, they basically cancel each other out, and it's the equivalent of doing nothing. So it's not, I don't want to say it's not important to think like that. It is pretty important, because I think when you can relate things back to things you already know, it makes it easier to grasp why we would want to do this in the first place. Okay, so let's jump into some examples. So I think that's enough theory for now. So in these first two examples, we're going to take a closer look at the first part of the FTC, so that thing where we had functions defined in terms of integrals. So this thing right here, we're going to look at that and we're going to talk about how to take the derivative. So for our first example, we want to find the derivative of g of x is equal to the integral from 0 to x of the square root of 1 plus t squared dt. Okay, so if we want to take the derivative, well, the derivative will undo the integral, and I just need to plug in x. So that's it. That's the derivative. So hopefully you don't have too many questions on that one, but let's look at a slightly more difficult one. So if we want to find the derivative of g of x is equal to the integral from 1 to x to the fourth of secant of t dt, you can view this as a chain rule, actually. So this is what I was talking about in the statement of the theorem when I translated it, and I said like, we might need a chain rule. It's not like as simple as just canceling. So the way we want to look at this is our outside function is the integral itself. So it's the integral from 1 to x of secant of t dt, and our inside function is x to the fourth. So notice x to the fourth is plugged in for x in the outside function. Okay, so this is just the chain rule you know and love. It's just the outside function again looks different. So just like, you know, when you were at first confused if the outside function was e to the x or tangent of x, well now we know how to do all those, so this is no different. It's just another function. So if I want to take the derivative of the outside function first, I know that it's going to undo the integral, but I'm going to get what's left over in the integral. So secant of t will become secant of x, but I don't want to just say x, I want to plug in my inside function, because that's what we do for chain rule, right? So I'm going to plug in that inside function, x to the fourth, and then in chain rule we then multiply by the derivative of the inside function, which is just 4x to the third. And so that's my derivative. So this is the hardest thing you're going to see with these types of integrally defined or functions defined in terms of an integral. You might see something where you have a different function plugged into the bound, and so it requires chain rule. But as long as you know your basic derivative facts, you should be golden. So as a reminder, just make sure you're still studying those and that you know them like the back of your hand. Okay, so now I want to take a closer look at FTC Part 2. So to do this, we're going to talk about the example of getting an IV or an IV drip. Okay, so this is sort of like the car example that we did in lesson 18, in that we can view an integral as sort of an accumulation of, in that case it was distance, in this case it would be amount of drug. So I've got your little picture of the IV on the very left there, and we've got the corresponding graph in the middle. And we've got some nice equations that give you a nice explanation on the right. Okay, so what I want to talk about here is why the fundamental theorem of calculus part 2 kind of makes sense. Okay, so let's imagine we have this graph, and I want to find the area between T1 and T2. So I want to find this dark pink area right here. And how would I do that? Well, if we think about, I like to think about it like a ruler. So if I gave you a ruler, so like, you know, ruler where you can measure things, and let's say it had, I don't know, 5 inches on it, because that's how many lines I drew. If I asked you how many inches are between, or how long is it between 2 and 4? So, okay, so let me rephrase that. So my question is, how long is, or what length is the ruler between the 2 and the 4 mark? Well, the way you'd find that, and you'd probably tell me very quickly, is you just subtract the 2, right? If I subtract 4 minus 2, okay, clearly there's 2 inches between 2 and 4. Well, integrals are no different. So if you imagine your x-axis as your ruler, this is exactly the same thing. So if we had put our ruler up here, and I said, how long is it between T1 and T2? Well, you tell me subtract the 2, right? So that's exactly what we're going to do. So it's basically like if you find the integral with respect to t2 and then find the integral with respect to t1 and then, subtract them, we should get the area in the middle. And that's exactly what this stuff on the right is saying. So it's saying if we take the area, let me re-highlight some things here. So if we take this area right here and we subtract off this area right here, we'll be left with that dark pink strip that's just colored yellow. So that's the idea of FTC part 2. We're finding a large area, we're subtracting off a smaller area, and we're left with that little strip in between the two x values. Okay? So some notes about antiderivatives. So the concept is not crazy. It's all the derivative facts that you know and love from lesson 7. However, there are a couple of things that are just a little bit different. So if I asked you, like, what function has a derivative of 1 over x, you'd probably tell me ln of x. But for picky mathematician reasons, when we take the antiderivative of 1 over x, we actually say ln of the absolute value of x. Okay, so that's really important. Don't forget that. The other thing, we kind of talked about this a little bit, is negative signs on the trig functions will be a little different. So for example, we already saw that the antiderivative of sine is negative cosine and not cosine of x. Okay, so that's going to happen with all of your non-co-trig functions, right? So now they're all going to be the negative antiderivatives, whereas your co-functions were the negative derivatives. Okay, so let's dive into an example, because I think that's when all of this theory is really going to come together and make sense. So our first example, we have the integral from 0 to 3 of 2 sine of x minus e to the x dx. So the first thing I want to do is take the antiderivative of each of these terms, which makes total sense that we can do because, well, we do the same thing with derivatives, right? So anything that applies to derivatives, since antiderivatives are just backwards derivatives, we can do anything that we did for derivatives with integrals, okay? So if I take the antiderivative of 2 sine of x, I'm going to get negative 2 cosine of x. And then the antiderivative of negative e to the x is negative e to the x. So we've done both of these antiderivatives already. It's not rocket science as long as you know your facts. The thing that's a little bit different, though, is we're going to indicate that we're going to plug in our bounds with a vertical line and repeating our bounds on there. So maybe I'll highlight that instead of circling because that'll be less confusing. Okay, so that part just means it indicates what we're going to plug in. Okay, so step 1 was just take antiderivative. All right, step 2, we're going to actually plug in our bounds. So I'm going to start by plugging in the upper bound. So I'm going to have negative 2 cosine of 3 minus e cubed minus, so now I'm going to subtract off the same function with the second or the lower bound plugged in. So we have minus 2 cosine of 0 minus e to the 0. So this step, we plugged in the bounds. And now we're just going to simplify as much as we can. This may not be required on a test, but it's always good to practice because you never know what you may have to do in Calc 2 or whatever. So let's just practice simplifying. So I can't simplify cosine of 3, so this is just going to stay negative 2 cosine of 3. I can't simplify e cubed, so that's just going to stay minus e cubed, but I can simplify this other piece of my function. So let's see what we get here. So we get plus 2 times 1, the cosine of 0 is 1, minus, or plus 1 if we're distributing the minus. So e to the 0 is also 1. So my final answer here will just be 3 minus 2 cosine of 3 minus e cubed. All right, and so this is our final answer for our integral. Okay, one more note. So we looked at an example that uses our basic facts, but I want to also talk about polynomials. So polynomials we know use the power rule when we took derivatives. So if we're doing antiderivatives of polynomials, well, we just need the backwards power rule. All right, or the power rule backwards. So what do I mean by this? Well, for those of you who remember cassettes and VHSs, what I mean is literally rewind the tape. So the way you do power rule, you do the backwards power rule exactly in reverse. Okay? So as a reminder, for the power rule, what we did was first we multiplied by the power, then we subtracted 1 from the power. So if we're doing the backwards power rule, okay, it makes sense then that the first thing we would do would be add 1 to the power and then divide by the new power, because we talked about our inverse operations. We said multiply and divide are opposites, add and subtract are opposites. And not only that, but I'm doing them in the opposite order. So this is literally the power rule. If we had it on cassette and we rewound it, it would be the backwards power rule. Okay? So let's look at a quick example. So for our last example of the day, we have the integral from 0 to 2 of 4/5 t cubed minus 3/4 t squared plus 2/5 t dt. Okay, so if we're going to do backwards power rule, we know our coefficients go along for the ride, so let's just jump in with 4/5 t cubed. So my antiderivative of this will be 4/5 t with a new power of 4 divided by 4. Okay, so I added 1 to the power, I divided by the new power. Now if I wanted to do 3/4 t squared, my new power will be 3, and I divide by 3. And if I want to do 2/5 t, my new power, my understood power on t here is 1, so my new power should be t squared, and I divide that by 2. And I indicate that I'm going to plug in 0 and 2 as my bounds. So just a reminder that vertical bar is very important notation-wise. Okay. So here we took the antiderivative. Okay, next we're going to simplify a little bit and plug in our bounds. So here, these numerators are each going to cancel with these denominators. And so when I plug in my bounds, I'm going to get 1/5 2 to the 4th minus 1/4 times 2 cubed plus 1/5 times 2 squared. Okay, so that's 2 plugged in. And now I'm going to subtract off the same function with 0 plugged in. And we're going to talk about it in a minute, because you're probably like, why are you even wasting your time doing that? But I'm going to do it anyway, and we're going to talk about it. Okay, so that is my function with the upper bound plugged in minus my function with the lower bound plugged in. Be very careful to use some parentheses around that second copy of the function so that you don't screw up the negative signs. So why did I go ahead and plug in 0 even though I know that this entire bit here is going to be 0? Well, it's a good practice to do when you're first starting out. So if you're a pro at integrals and you're like, oh, I can recognize very easily when a function goes to 0, not super necessary to write all that out. However, I caution you, because there are some functions that when you plug in 0 are not zeros. For example, cosine. And we already saw that, right? Cosine of 0 is 1. So if you do that too fast and you're a novice at these, I don't want to see you lose points just because you were too lazy to write down some extra terms, okay? So especially if you're a novice, make sure you're writing out every single piece of doing the subtraction, you know, with the bounds plugged into the function. Okay, so let's simplify just a little bit. So here we plugged in the bounds. And so if we simplify, we get 16 over 5 minus 8 over 4 plus 4 over 5. So if we add this together, we get 20 over 5 minus 2, which is 4 minus 2, which is 2. Okay, so here we just simplified, and our final answer is 2. So hopefully now you have a nice introduction to the fundamental theorem of calculus and definite integrals. So the last thing you need to do today is just check your understanding. Make sure you can answer the question, how are integrals related to derivatives? And that's the end of lesson 19. Just 2 more to go.